to be talking about data analysis for untargeted metabolomic studies. So we've been talking quite a bit about what mass spec is all about, and some of this may be a little repetitive, but I don't think so. I think it'll be a little bit new. So the objectives for today are just to understand how we analyze and align your untargeted metabolomics data, what quality control measures we use for untargeted metabolomics, and to understand an untargeted metabolomics data report. Where we are in the process, we've already generated all the data, and now we're just looking at the data before we're really able to do statistics. I'll show a little bit about how we might do some statistics, but not much. That'll come later today. Okay, so there's a kind of a complicated flow chart here about how we do the data analysis, and I'm going to be kind of skipping forward and back on this flow chart. But to start with, we have raw mass spec data. And the next thing we're going to do is we're going to do what we call molecular feature extraction. And so I want to define again what a molecular feature is. We had Gary Patty here on Monday, and he talked about there being 14,000, I can't remember the word he used. He didn't call them features. Maybe ions in your mass spectrum, and how when you start reducing that down, you get to maybe 4,000 metabolites. So what a feature is in our situation, we sort of begin to reduce that mass spec data up front by saying, okay, if I've detected 100 ions coming out at any one given retention time, how many of those ions can I explain as belonging to the same compound? And at a minimum, a feature would probably be a parent mass and 2 or 3 isotopes that we know belong to it, which you have seen some figures of in the previous talks. So from there, I'm just going to skip the rest of this slide and just show you kind of a little bit more about how we do that. So I want to make a point. Showed some spectra yesterday from a targeted data analysis, and this you recognize as the glutamine with the molecular ion and the 2 isotopes that we were able to detect. And this is a very limited mass range, so I'm not trying to compare this to this, but in a targeted analysis, depending on how you do, how we do the extraction of the compounds out of your sample, we'll have a pretty clean spectrum. There may be just, a few peaks that we're looking for. Whereas in an untargeted analysis, you're going to have something like this. So let me go back and talk about the total ion chromatogram, which is up here. Just some terminology. So the total ion chromatogram is the sort of the sum of the intensity of all the signals hitting the detector of the mass spec at any given time. So this is, reflects your chromatography. You have some things coming off early, and then you have peaks that come off later. And I also want to say that a total ion chromatogram can be dominated by a few pretty large peaks. Those are things that are very, very highly abundant compounds, some of your amino acids and things like that. But even where it looks kind of relatively flat here, there's definitely ions coming out at that time. They may be lower intensity, but there are definitely things there. And one of the things I can do right here is I can sort of highlight a part of the chromatogram and tell it to extract and sum up, all the ions that are coming out during just that 0.2 minute window or whatever the case may be. And when I do that, I get something that looks like this. So again, this peak here, you can't see it because of the mass range, but it has, all of its isotopes that go with it are there. They sort of probably look like one big thick band here at the bottom. And the mass range we collect data over is from 50 to about 1,000 Daltons. We don't go any higher than that. But in terms of the actual number of features here, meaning just if I just at this point define a feature as the molecular ion plus the isotopes, how many there are really can depend on a few things. It can depend on a cutoff. I might decide that I want a certain signal of noise for the peaks I'm picking, or I might decide that I'm just going to have an arbitrary intensity cutoff. I'm not going to accept anything that is less than, 1,000 counts on this scale. So when people talk about, how many features they detect, there are all these decisions that go into that, like how are we extracting the data out to begin with. And so, there could be anywhere from, 50 to maybe 100 actual features here. So yeah, some of the stuff that looks really, really low, those are real metabolites that we need to figure out what to do with. Okay. Okay. So like I said, we are using a way of trying to collapse the data a little bit ahead of time as opposed to just processing everything and trying to reduce the data later. This software comes from our instrument manufacturer, which is Agilent. And what it will do is we can tell it which of the most common ions, addicts, and I'll explain what addict is in a minute, that we expect to see. So an addict is basically an ion that is associated with your metabolite of interest, which is generally how it gets ionized. So if it picks up a proton, it becomes a singly charged protonated form. If it picks up sodium, same thing, it's still singly charged, but will have a mass that's 23 Daltons higher than your compound, etc. And you pick up sodium and potassium generally from glassware, because it will leach out of the glass. And then something like ammonium, the ammonium ion, you would pick up if you had that in your buffer, in your HPLC buffer. And then similarly, in negative ion mode, you might expect to lose a proton or gain a chlorine. So let me show you what that looks like in the next slide. So, we do in our workflow try to collapse as many features as we can on the first pass. And we will, so the software itself will go and decide, it sees something that it thinks is molecular ion, something else that it sees that's 23 Daltons away, so it assigns it as sodium. Something else it sees it's 38 Daltons away, which assigns as a potassium. And then even down here, it finds two of the molecular ion plus a sodium associated together. And again, all of these have come out of the HPLC at the same time, and these ions are formed in the source of the mass spectrometer before they travel down the flight tube and get detected. So they will all have very similar, if you were to do an extracted ion chromatogram of this, it all have the same peak shape, the same centroid retention time, and that kind of thing. So the instrument is pretty successful at peeking those out. So it will take all of these ions and it will sum their intensities and collapse them into one feature. So we've eliminated 14 or 15 peaks in the spectrum and reduced it down to one peak. Notable here is that for this particular compound, the sodiated peak is much preferred to just the protonated peak. In other words, this molecule likes to pick up sodium and could be fatty acid or something of that nature. We know some classes that prefer sodium than hydrogen. So hopefully that helps you see why we want to do some of this feature detection up front and collapse some of these ions together. You're going to hear about some alternative ways of doing this as well. So there's different theories on how to do this out there, but this is our basic workflow. And I just wanted to make the point. So, the software in our hands will kind of give us a nice little output of what all those ions were. It collapsed into that feature. If you have a report from us, you've already done data analysis with us, or you're about to, the page where you'd be able to find this information on your report is called the Annotations tab, and it tells you what the molecular ion was, and then all of the features, all the ions that went into making that feature. Okay. So I'm going to talk a little bit more about subsequent data processing we do as well. So just talked about how we do the first step. So the next step is let's take all the features that the software has been able to detect and maybe do a little bit of filtering on it. We generally we filter out anything that isn't present in at least 70% of the samples in one group. So when you give us your factors, control and case, whatever the case may be, we'll put those into the software, and then it will go back and find out if that particular feature is in 70% of one group. So it could be in 0% of your control and in 70% of your case, and that's okay, because there may be a situation in which, you know, that's what you're looking for. You're looking for that very clear biomarker that's really only an indicator of your treatment, whatever that may be. That's not the most likely situation. The most likely situation is that it's, you know, more intense in one group than the other, but usually not completely absent. Oops, sorry. So the next step is, you know, take these features and try to map them to known compounds. The way that we generally do that is we have a library of over 1,000 authentic standards here in the MRC squared. So we have taken all of those standards, run them on our system, and we know, you know, their accurate mass, the retention time, as well as how they present themselves in the spectrum, whether they tend to be primarily sodiated or primarily protonated. And so, you know, essentially, the first thing we're going to do is a mass and retention time match against our library. I'll talk a little bit about this a little bit later, and I'll come back to this slide. Hold on, let me go forward a minute. Okay, well, no, I'll talk about it now. So one of the things I wanted to point out here is, as I mentioned yesterday, the software also has the ability to go in and to sort of predict or create a potential formula for a compound based on its accurate mass and its isotope pattern. And in previous reports, we have done that. So some of you guys have received data from us. You will have seen a report that contains formulas. Likely going forward, we will not do that, and I'll explain why a little bit later. If you have a report that contains all these formulas and you want, for whatever reason, to go back and try to do some additional data mining on that by sending it through a database search such as Metlin, which I'll talk about how Metlin MSMS today. I never did show the Metlin website for the rest of you, but it's the same place as the MSMS website, which I'm going to talk about. If you want to do that, we can certainly help you do that. It's just a matter of linking up your formula with what's on our annotations tab within your data report. The reason that we're probably not going to do this going forward is when you have small molecular weight ions, the number of possibilities of atoms are low, and so your confidence in the formula is quite high. As you start to get into the larger masses, you have more combinations of atoms that are possible, and when you add phosphorus and sulfur and maybe chlorine into the possible choices of assigning a molecular formula, it gets a little bit more, it gets a little bit less confident that that is assigned the right one. So we think there are better ways to handle that data, and so we'll certainly help you with that. So just to go on with the typical data report. So some of you who have data from us, again, some people come to the workshop because they've already received data and they want to learn more about how to do the data analysis. So for those of you who haven't seen it, it'll be new, but you'll have sort of your samples across the top. This column here called frequency is how often that compound was detected. So a frequency of 1 means it was detected in every sample and every pooled sample. We talked about how we do pools yesterday. And then in this case, we sorted all the features by putting the named compounds first. However, more typically, if you didn't sort by named compounds, but you sorted by most intense compounds, you'd see something like this, where you would have, again, your samples across the top, but over here, you have a combination of named compounds, compounds for which we've assigned a formula, and some compounds for which we could not assign a formula. There was nothing that the software was able to do to kind of rectify that mass with any formula. Given the choices we gave it, we told it, you know, there might be sulfur, chlorine, potassium in these, but if if it were something else like a bromine, it wouldn't be able to find that formula. So kind of in the future, you'll see mostly this, and then we'll go out and have different ways of trying to find those formulas than the software here. So this is fairly typical on a first pass. A lot of the most intense ions are not named at this point, and we're going to talk about why that is, and some of that is issues that Patty talked about on Monday, and how we're dealing with that in the future. Along with your report, you will receive a QC report, which is going to tell you about the variability of our internal standards in the samples, in your samples, and over the 100 samples you run. What was the RSD of each of their internal standards, which gives us some measure of the confidence. Typically, too, and I think it's way over in the sun, so I kind of cut it off. We will have calculated RSD of all the pooled samples we ran for you. So again, the pooled sample is we're going to take your sample, pool it, and run it about every 10 injections. So we might have, by the time we're done, 10 replicate injections of that same sample, and RSDs on those are typically low. Typically, I would say 60% of the data, probably 100% of the data that shows up with a frequency of 1. Okay, that's a bit of an overstatement. Probably 90% of the data that shows up with a frequency of 1 also has an RSD less than 20% in the pools. When you start getting into high RSDs, it's typically because of missingness, the compound wasn't detected, or the signal of the compound's so low that the integration wasn't as good as it should have been. Okay, so again, going back to the sample report and how we have a lot of unknowns here and just a few named compounds. As Gary Patty talked about on Monday, we've known for some time that there are a lot of what we call redundant features in the data, and those are events that happen usually in the source of the mass spectrometer. So not only was that your metabolite of interest able to pick up the 4 choices we gave it, a proton or a sodium or potassium, but also it might pick up additional associations. Gary showed one where there were 2 compounds that were colluding, that were associating in the gas phase and being detected together. That happens. You can't necessarily give the software, when you're selecting the features, too many computational choices. I want to consider that there could be 3 of the molecular ion associated with 1 sodium or that kind of thing. So if you don't give it too many computational choices, then some of the things it's going to detect will truly be associated with that compound, but we just didn't collapse them into that feature, if that makes sense. So again, known versus unknown metabolites, sort of definition of this is interesting. Gary showed the sort of graph where he mapped the KEGG pathway and known and unknown, how many things were really truly unknown. But in my case, I'm using the definition unknown as not matched against a library, our authentic library at this point. So these are things which we have to go figure out what they are. Potentially, we will be able to maybe do MSMS and figure out what they are, or another option is to go out and buy the authentic standard if we're pretty confident that this is an unknown that's showing up all the time and we want to add it to our library. A third choice there is, even before we do MSMS, there's a lot of information in our correlations calculations that we've been beginning to do, which I'll show a little bit more about in the next slide. That may tell us what class of the compound is already before we start to think about doing MSMS or buying an authentic standard. Which actually brings a point up. People, I think, may have asked this question last year: why don't you just do MSMS on all of these unknowns, for each data set? as I'm running your samples, why don't I just go ahead and start doing an MSMS on everything? And I'm going to show you a slide in a minute when you see what MSMS looks like. That what's likely going to happen if you do that is you're going to be missing things, because the time it's taking to scan through and do MSMS on the peak it just detected, there's other stuff coming off, the mass spectrometer that it's not detecting because it's in the mode of doing a fragmentation instead of in the mode of collecting, the MS data, the raw feature data. So we don't do it automatically on every sample. The philosophy is to go ahead and analyze the data, do the statistics, and then go back and find out the identity of any unknowns that are statistically significant for your samples. It's a very efficient way of doing it because why do MSMS on everything if it's not even significant to your your question, your biological question you're trying to ask? And also, like I said, we'd be missing data. So, there are other tools out there to do this data reduction. We created our own because we wanted to figure out whether our data, because we do it slightly differently than other people do, the way we process it up front, whether there was a benefit to sort of doing our data reduction through using our own tools. We did this. We have a data reduction program which is based on binning. So in other words, everything that falls within a certain retention time we consider to be possibly correlated or possibly related to each other. Those could be redundant features. And then cluster analysis. So even some things that fall within the same retention time are going to be different because there are more than one metabolite coming out and co-eluting from the HPLC at any given time. And then we apply chemical knowledge to eliminate redundant peaks. So can we explain what all of those additional peaks are that we're seeing? And this could be an example of what it looks like. So we have sort of binned the data according to retention time, and then we've clustered it by correlations analysis. So we have, we've calculated the correlation between this compound and this one over here. So this, and then all the other compounds in that bin across to the right. And then the one where it's actually correlated with the salt should be a 1. So 1 versus 1, 2 versus 2. And then we've, like I said, we've clustered it. So now, even though the retention times may not be identical for all of these, they're put into an appropriate form that allows us to sort of look at them as a whole, as one whole thing. And we, like I said, we try to go through and calculate mass differences from what we believe to be the molecular ion, the main compound of interest, and try to explain, all of what they are. Goes into a little bit more detail than you might want to know, but if you're reading papers or you're really interested in this topic, in addition to picking up addicts, sodium and potassium, etc., within the mass spectrometer as well, in the source mass spectrometer, the compound can fragment right in the source before it gets into the mass spectrometer to be detected. So it's going to have exactly the same retention time as the parent ion, but it will be detected at a different mass. And so those events are, can be known. It's essentially kind of doing a pseudo MSMS right in the source of the mass spectrometer. And sometimes you can use that information. You could sort of take this information and put it into an MSMS search and get some matches on that. So again, we would, if we can explain all of the things in this bin, we can eliminate 3 out of 4 of them and provide you with a data report that just has the one molecular ion, the most important metabolite. Which, why would you want to do this? And I think hopefully, I don't know if some of the statistical speakers today are going to talk about, when you have more features than you have samples, you have to jump through more hoops in your statistics. And so and that's always going to be the case, but to the extent that we can eliminate features that are not important, then we can, hopefully, get clear results on those compounds that are statistically different between your groups. And this is just kind of a blown up example of something like tyrosine, where again we can explain every peak that is associated with it. Well, one I call unknown 345. I can't explain it, but I've seen it over and over and over again, and it's an addict that attaches to different to different features within the mass spectrum. So I just kind of want that looks up close. Okay. So going back to the data report that we send you, at this point, some of you who have data reports from us will have actually had some of the statistics done within the Agilent software. The Agilent software is called MPP, Mass Profiler Pro. Let me skip forward a little bit and I'll show you, for those of you who have seen it. So you may have seen a report that actually has like a PCA plot. Generally speaking, we provided the PCA plot if we saw separation, and if we didn't, then we didn't provide that. But so if you have that, that's great, because those are truly features that we can go back and try to figure out what they are. But I actually suggest to everybody here that as we get this data cleaning process in place, that we think about using some of the other online tools that are out there to do more data analysis. I don't think once we do this data cleaning, we can feed that back through MPP, but unless I talk to Agilent and they figure out some way of doing that. But we do have a lot of other tools out there, and those are some of the tools that you're going to use in the hands-on sessions tomorrow, as well as I think there may be some lectures about them coming up yet today. So my recommendation is that we do the data cleaning process, you take that reduced data set, and then go back to one of these online tools and do some of the statistics on it. Or get a statistician from your department to help you with that. But I would definitely work on the cleaned up data set at this point. So again, just to be clear, in each one of these blocks, we're probably going to end up just picking 4 things out of the 12 or 15 that are there. So it's going to significantly reduce your data set. Yes? We will be in the future, but if you have a historical data set, we'll have to go do this process for you. Yeah. Yeah, yes, very new. So, right, so does that make sense? Yeah. No, no, and eventually what it'll be is it'll just be different tabs of the same report. You'll have the raw data, and then you'll have the cleaned up data. So we never really eliminate anything. We're not going to throw it out, but the cleanup tab will be the one you'll probably want to use for your. Yeah, we're still trying to automate it. I'm pretty much doing it manually at this point, but it's not hard now that I've gotten used to it. Took me about maybe 4 hours to clean up the whole data set. And we're still investigating whether some of the other tools out there might be faster and more efficient. But we do know that given the way that we do things and we collapse some of those features up front, this might be the best way for us to do it. And interestingly, it's given us so many more targets and so much more information about those compounds that are molecular ions that expect to expand our library by half this summer. To go through and identify all these unknowns. So maybe in the future you'll just get a knowns report, not an unknowns report. Who knows? Right. So like I said, I recommend that we take the cleaned up data and go outside and do some online searching. So just to be clear, Gary again talked a little bit about knowns versus unknowns, and so there are a lot of different signals in the mass spectrometer, or even after we've cleaned this data up and we've removed all the redundancy, you're going to have these types of classes of things that are still there. So metabolites of interest, those are clearly the ones you want to see. Maybe drug metabolites. These can be pretty difficult to do even an MSMS match on, because I don't think they're all in the databases. You know, a lot of times you'll find a drug, but then you don't necessarily find its metabolites in the databases. However, if we were to find a drug in, you know, and then find, for example, something that's highly correlated with it, and we can maybe explain that it's one of the drug metabolites, we'll do that. Background ions, not that many, but there are a few things that, you know, they're one of the previous slides, a couple of the ions there that you'll see are there because we use them to calibrate. We have to have something so that we can keep the mass accuracy of the instrument continuously updating. There will be some contaminants sometimes, you know, a few phthalates, but, you know, polymers, rarer now, but I think before people became aware of different, you know, things, recommendations that we've made for how to treat samples. In the early days when we were doing this, you know, we would see a lot of polymers coming in. PEG, polyethylene glycol, is something that we would see. You know, maybe important to sort of make sure that you, if you're doing gel work for proteins, that you sort of do that in a different place than you prepare your metabolomic samples, because some of the compounds that are used in gel work can, if they contaminate your metabolomics work, can really show up in the mass spectrometer and be very, detergents and those kind of things, they can be fatal to your experiment. I mean, we can go back and try to eliminate them, but they can be fatal. So you know, just make sure you have a very clean area when you're preparing your samples, and especially if you're, like I said, you're doing a lot of that type of gel work, keep it in a separate lab or a separate bench at least. You know, some of the unknowns are peptides, and we're in the process of identifying those anyway, because we feel like those could be important. All right, so you have this cleaned up, reduced data set. You've gone through and you've put it through, say, Metaboloanalyst or one of the other tools that we're going to talk about. You come up with some knowns that are significant and maybe still some unknowns. So what's the next step? The next step is to try to identify those unknowns, you know, either by MSMS or by buying an authentic compound to match it to. So just to review how MSMS works. So, sorry, hold on one second. Can't see that very well. Right, okay, so it's not, this picture's not perfect, it's not great, but you create your ions in the source, and instead of just sending them all the way down the flight tube to the detector, what you'll do is you'll put them through this quadrupole mass analyzer, which Charles talked about on the first day, and you're basically going to select one of those, and the rest are going to get ejected, and then the one goes into a collision cell, and it will get fragmented, and then all the fragments of that compound will start to travel down the time of flight and then come out as a mass spectrum. So in an MSMS spectrum, usually the highest mass is the parent ion, because everything else is a fragment of it, so it's smaller. So you can sort of read a MSMS spectrum from the right down to the left. The only time that's not true is if the thing that ended up in the collision cell is really a doubly charged ion, in which case when it starts to fragment, I'm sorry, yes, in which case it may have presented itself as a mass of like 400 in the mass spectrometer, but it was really a 900 Dalton, you know, small peptide. And then when it fragments and everything is now singly charged, you may start to see peaks at 700 and 800 and 900. And that's easy for us to pick out. We know when we see that what's going on. Oh, I'm sorry. Oh, so this is normal operation, but this would be, you know, an MSMS operation. And same thing, like you said, we pick out one of those ions, we trap it, and we collide it, and then we send it down the mass spectrometer and pick up the fragments. Okay, so I talked a little bit earlier about why we don't do MSMS on everything. And so this is your TIC that I showed earlier, total ion chromatogram of everything coming out. And then this is a fairly robust targeted MSMS. In other words, I've gave it at quite a few ions that I wanted to detect. And as you can see, sort of the signal for the MSMS is a little bit lower, but you can see where it's sort of done MSMS on some of the most intense peaks here, and then what that looks like. So given in any one of these MSMS chromatograms here, if I were to extract all the ions out of there, it would look something like this, where I would have, like I said, the most intense peak, and then all the fragments from it. And you take the peak list from here and you submit it to an MSMS search. So there are quite a few tools for doing this. One of the ones I like is called MetFrag, and it's there's two different ways to do kind of MSMS database searching. One is you can try to match your spectrum against a library where other people have done MSMS, sort of curated it and said, these are the real peaks that come from that compound, and uploaded those to a database. So Metlin is, again, going to have a lot of MSMS spectra in there, so you might be able to match your MSMS spectrum to there. On the other hand, another way of doing it is sort of to take a program such as MetFrag, which takes the theoretical mass of your compound. So it goes and it takes this mass, it finds all the possible molecular formulas it can find in a certain database, CAG or whatever the case may be, and based on the molecular formula and the way the atoms are attached, the actual structure, it predicts what fragments would appear. So this can be a little bit more complete, because there isn't an MSMS spectrum out there for every compound. People have uploaded quite a few, thousands, but you may still have a compound which is legitimate, but there's no MSMS spectrum for it. So this is just another way of saying, well, in theory, if I had this structure and I gave it this much energy, it would break up into these fragments, and can I match that? So it will tell you, for example, what the structure is, and then how many fragments it was able to match. And then if you go further, I thought I showed, I had another slide where I showed what the fragments were. And so an analyst who is familiar with this type of work can say, yeah, those fragments make sense, or no, they don't. I mean, generally speaking, they do, because we've put a lot of work into refining the algorithm for how these things should break up. And like I said, Metlin is the other one of several other online tools where you would just upload the MSMS spectrum, so all the fragments, tell it what the parent ion is, and then see if it can match an actual MSMS spectrum. And the nice thing about that is, if it does find one, it gives you sort of this figure where this is your MSMS spectrum and this is the one it matched against. So you can really look at how well those peaks align and say, wow, that's pretty good, because my most intense peak was this, and so was this one. Now, they had a few peaks that mine were much less intense, but that can depend on a lot of things about the instrument. Which instrument it was run on, how aggressive the energy that was put into it was to break it up, and things like that. So they're both good tools, but that's basically how you would sort of start to begin to identify unknowns. Just get a tentative identification based on that. There are a lot of other things that can go into it. Some of the correlations analysis, how well does it correlate with other compounds in its class, and things like that we expect to see that can help identify it. And like I said, for those of you who have historical reports, if you did get PCA plot, and then you have the associated data with that, like a fold change analysis, we can certainly look at what some of those compounds are doing MSMS, but probably before we do that, we would go back and do the data reduction, and then redo the statistics for that, because we find that new workflow just makes things much clearer as to what's going on. So, okay, one thing I do want to point out, and I think it's when you get a data report too, for the named compounds, just keep in mind that if there are isobaric compounds that we're not able to separate in the mass spectrometer, then the way we are going to handle that is we're going to report the most biologically likely candidate. So, we had at one point kind of, put slashes and told you all the possible things it could be, but we just now report the most biologically, biochemically probable version. So if you have any questions about that, just talk to one of us. We do some preliminary screening where we try to reduce some of the redundancy, but our new process does even more of that. If we see the same peak in both positive and negative mode in the mass spectrometer, we'll only report it in the one mode where it was showed up the best. So either had the lowest RSD or was most intense or something of that nature. So, so if you have any questions about this, about your named compounds or something we saw in positive, we didn't see a negative, and you're confused about that, this is why. So, and that's all I have for today. So I can take questions, I think. All right. So, questions? Yes. Yep. And everybody, please use the microphones. He asked if it was common to have dimers or trimers. Yes and no. The more ionization events you have, that is somewhat dependent on the concentration of the original sample. So, in other words, if you think about it from sort of a statistical point of view, if I have X amount of this compound and energetically, there's all these events that could happen, like a bell curve. Even those ones that are not likely to happen, that are at the ends of the bell curve, the more samples, the more of ions I have of that, you'll see them. So the more intense the peak to begin with, the more likely you are to see some of those events like dimers and trimers. And also, go ahead.
Is there a way to remove them using the software?
Our software we could tell it to look for those up front. But again, even using the redundancy removal software where we're doing the binning and the correlations, it's pretty easy to go back and once we've determined what the molecular ion is, explain all the other peaks, and then we'd know exactly which ones are dimers and trimers. That makes sense? Okay. Other questions? Okay. You first. Okay, go ahead.
It was never clear to me, are you combining positive and negative ionization for the same analysis? I mean, statistical analysis?
At this point, yes. But again, in our new workflow, usually I take the redundancy removed compounds and pass it to a statistician. So actually, I could ask Ala, what would you do in that case? Would you combine your negative and positive data before doing like PCA analysis, or?
Part of the problem is that what Maureen said, we're in a process of changing our data analysis pipeline. So we're trying to get the best and cleanest data set to you. And so there's a little bit of a confusion. I think what our workflow is going to be is we will do redundancy, this sort of data reduction for positive and negative mode separately first. And then for all the remaining part of the analysis, I think this should be combined really.
Yeah, and I mean, George might speak about this too, as to normalization across the different modes and such. Can't claim to be an expert on that, so.
Yeah, quick comment on that MSMS
Mm-hmm.
strategy. So I totally agree with you that you cannot really do too many MMS inline, but there are also other considerations. So for low abundance metabolites, you may never have enough ions to do fragmentation.
True.
Then the MSMS collection window is usually larger than profile mode. So if you use 1 Dalton or even 0.1 Dalton for collecting the ions,
right,
that usually gets multiple ions in the same trap.
Right,
so
exactly.
Then you get a mixture.
Right, exactly. Right, yeah.
That also compounds the adaptation.
Right, exactly. So what he's saying is you can actually tell the quadrupole, which is sort of selecting which which ion you want to do MSMS on, that you've probably told it in this case if you're doing a targeted MSMS. And you can leave that window open to 4 Daltons, in which case you get an R instrument, in which case you get more intense signal, so you have a better chance of getting a result. Or you can narrow it down to about 1 Dalton, in which case you're really just getting your molecular ion, but that has, like he said, the possibility of really having a much more difficult time getting a good enough intensity in your spectrum to get a result. So there's kind of a trade-off there. Thank you. I have another question in the back.
Could you explain more about how you do the binning process for?
I'm sorry, say the word one more time. The what process?
Binning.
Oh, binning.
Yeah.
So Ala and Bill Duran talked a little bit about that. I mean, the binning part is pretty straightforward. What we actually started looking at was just a retention time gap, because it turns out that, so that's why we have clusters within bins, because there, you can always find a very small retention time gap as things kind of come and go. But, at some point there may not be a gap that's big enough, and so we end up with, multiple features in one bin. But it was enough of a reduction of the data set for us to be able to then go back and cluster it and say, okay, yeah, I can tell there's just 4 things here, as opposed to doing the clustering on like the entire data set. Does that adequately explain it, Ella? Yeah, okay.
So,
you want to go back to that slide?
No, I think it's fine. The only other thing that I might add is that this is sort of semi-arbitrary at this point. I guess, the concept is really what we heard about a lot in the previous days when we talked about chromatography. I mean, essentially the compounds, like, if these are the addicts or the fragments of the same compound that tend to, basically, they'll have, the idea is that, the things that have similar retention times,
So do you have a retention time cutoff to find the bin?
Right, so what we did is we initially took 0.05 minutes as a gap that we're looking for. So in other words, if I have something that's 1.05 and then something that's 1.12, those would separate into 2 different bins, because there was a gap of 0.05. It was somewhat arbitrary, but it was something where we were able to verify that not only, it turns out our software through this recursive analysis is very good at determining retention time for all of the addicts that come with a compound. So in other words, if I had phenylalanine and then I have phenylalanine plus sodium, those are going to be probably 1.398 and 1.397. So about 0.001 difference at the most. So that's why they always fall into the same bin. We don't have to worry about compounds splitting across bins, because the software does such a good job of determining the retention time in the first place. And again, that's a macro feature of the data. And any given individual sample, that might be slightly different, but the part I kind of skipped over, which is called alignment, is where it finally decides what is the average retention time for that compound in all the samples. So that's why it's so reproducible. Does that make sense? Okay. So, any other questions? Thanks for your questions. That was really good. Thank you.